Hello everyone. In this lecture, we shall take forward our discussion on retarded potentials. In the previous lecture, I had introduced the notion of retarded potentials. That is, uh, if I have a charge at a certain point and I want to find out the field, the potential due to the charge at some other point, we need to consider where the charge was, the position of the charge at an earlier time, which is known as a retarded time. And this concept of retarded time led us to the notion of retarded potentials, and we showed that the retarded potentials, they are indeed legitimate because they satisfy the inhomogeneous potential equations. So in this lecture we shall take this idea forward and obtain what is known as Liénard-Wiechert potentials. So basically what we'll do is we'll take the concept of the notion of retarded potentials, and we will apply it to the case where a point charge is moving along a certain trajectory, and potentials that we derive by applying the idea of retarded potentials, that will be the Liénard-Wiechert potentials. So this is basically the idea. So let us consider that I have a charge particle which is moving along this trajectory, which is shown by this curve. So right now the charge is over here, and I want to find out the potential at this point, the potentials, the scalar as well as the vector potentials at this point, small r. But I don't have to consider, because from the notion of retarded potentials, it is not the potential due to this position that matters. It is the potential due to an earlier when the charge was at an earlier position. Okay, because the information that the charge has moved from here to here, it takes a certain finite amount of time, and that finite amount of time that it takes is simply the distance between the retarded potential and the field position, which is r divided by c. So if the present time is t, then we need to consider what happened at a time which was t minus r by c. So if I have, let's say, a particle, okay, a charged particle, and that is moving along a trajectory, and that trajectory is given by w of t. That means w is a set, basically w is a set of vectors, and these vectors will depend on time t. So we need to consider what was the vector at the retarded time, w at tr. So the retarded time is given by this particular equation, that is small r minus w, which will give us the separation vector, magnitude of that, which is equal to c into t minus tr. So here capital R is of course the separation vector, and it can be shown that the effect of retardation, okay, the fact that we are taking this, we are considering at an earlier time, or the retarded time, the effect of that consideration is that it will extend the charge. So if I have a point charge, that point charge will seem to get smeared, okay, and from a point charge it becomes something like an extended charge. Okay, so that's the effect that the retardation is going to produce. And because what happens is, if I try to, suppose I have a charge distribution and I want to find out what is the total charge contained within this distribution, then if I try to integrate over this entire volume, because the entire volume is also moving, so the total charge that I calculate will turn out to be more than the actual charge that is contained within that volume. So that means there has been a change by a certain factor in the charge. Okay, so this factor is 1 minus r cap dot v by c to the power minus 1. So this is the factor that we'll have to multiply when you are trying to compute the total charge. There is a very nice geometric proof which is given in Griffith's third edition, that is in section 10.3.1. You could just refer to that. I don't want to discuss this separately over here, because that is more or less it's a geometrical proof, but it's a very good read for anybody who's trying to understand what's happening over here. So he takes the example of a train and an observer who's watching the train, and considering the fact that light travels at a finite speed, he shows that if you're trying to find out the length of the train will change. From the actual length, the observed length will change by a factor of 1 minus r cap dot v by c to the power minus 1. So this is basically the effect of retardation. So all we have to do is, if I want to find out the total charge, so I have some charge which is over distributed over some volume tau prime, then I want to find out total charge. That means I'll have to integrate over the entire volume. That integration over rho will give me q divided by 1 minus r cap dot v by c. Of course, here we are considering a point charge, so the total charge is q. And because of retardation, this factor comes into the picture. So this is what we have to keep in mind when we are trying to find out the Liénard-Wiechert potentials. So first thing that we need to do is we need to find out the scalar potential, so phi at r comma t. So because we are considering the effect of retardation, so we can consider the point charge to be a limit of an extended particle. So we have to basically make a replacement like this. So we basically take a point charge and replace the charge q with q times this factor. So the potential at any point, we already know the formula for potential. Potential is simply k q by r, so 1 by 4 pi epsilon naught q by r. And because we are taking in the effect, we are considering the effect of retardation, it will not be q, it will be q times 1 minus r cap dot v by c to the power minus 1. So this will be the potential. So then what you do is I just brought this down into the denominator, then add these together, this one minus this quantity, and take the c into the numerator. So that will give us the phi is equal to 1 by 4 pi epsilon naught qc divided by rc minus r dot v, where v is the velocity of the charged particle. So let's call this as equation number 1. Now we need to find out what is the vector potential A. So the current density due to a charged particle moving with suppose I have a charge density rho which is moving with a velocity v, then the associated current density is given as j equal to rho into v. We have proved this in the class earlier. And at present the vector potential, it becomes this. How did we get this? Because we know that A is equal to mu naught by 4 pi integration of j d tau divided by r. So j is equal to rho into v, so that's how we get this expression. So this is the vector potential at point r at the present time. So now over here I take this v and r, I take this outside, and what will be left inside will be simply rho. Okay, which is because this is integrated over the primed coordinates only. So what will be left behind is rho, and the integration of rho, we know that it will give us the total charge, and the charge here is q. But because we are considering retarded time, the effect of retardation is to whenever you're trying to compute the charge, it will be charge times that same correction factor, which will again appear here also. So we again simplify and we write it like this. And now what we do is we just do a little bit of manipulation. So this mu naught, we write it as 1 by epsilon naught into c square, because c square is equal to 1 by mu naught epsilon naught. So mu naught is equal to 1 by epsilon naught into c square. So we keep the 1 by c square outside, then this v we keep it again outside, and everything else we just club them together, and we can immediately recognize this. What is this? This is nothing but the potential that we had obtained. So v by c square into potential. So if we know the scalar potential phi, we can find out the vector potential also, provided we know the velocity. So we have the scalar potential given by this and the vector potential given by this. And so for a moving charge, these equations 1 and 2, they are known as the Liénard-Wiechert potentials. So let's stop here for the time being. So this is the Liénard-Wiechert potentials. The next step that we need to do is we need to use this Liénard-Wiechert potentials to find out the electric and magnetic field, because like I had mentioned in a previous lecture, I think it was the lecture on gauge invariance. it is not the potentials that we are actually interested in. We are interested in ultimately the electric and magnetic fields, because the potentials, the scalar and the vector potentials, after all, they are just mathematical constructs that we make in order to simplify our understanding of the problem. But the physical reality always lies with the fields. So we are ultimately interested in the fields. So we have got the potentials, well and good, but the next thing that we need to do is we need to find out the associated electric and the magnetic field. So that we will do in the next lecture. Thank you.